Hey guys, we're going to actually look at the last lesson of this school year, which is about the empirical rule and more to do with the normal model and finding probabilities. Again, the normal model allows us to calculate probabilities and use those probabilities to determine if a data value is surprising or unlikely or completely expected. What the empirical rule does is it kind of breaks down those probabilities for us. So the empirical rule tells us that the percentages of data in a normal distribution, so again, the data do have to be distributed normally following the bell-shaped curve. What this tells us is that 68% of the data values will fall within one standard deviation, so from -1 to 1. 95% of all of the data fall within 2 standard deviations, so from -2 to 2. And then 99.7% of the data will fall within 3 standard deviations. What this tells us is that really the majority, and oftentimes 100%, fall within 3 standard deviations, which is why I kept saying and keep saying that being outside of 3 standard deviations is really surprising and very unlikely to happen. These percentages are talking about the middle of the data. So it's the middle 68% and the middle 95% and the middle 99.7%. Because it's in the middle, that means everything is distributed evenly. So like this area here and this area here, they're equal. In fact, they would each be 34%. Because if we take 68 and cut it in half, we end up with 34 and 34. The other really cool thing that using this rule does is it allows us to figure out easily what percentage of the data is above 1 standard deviation, or 2 or 3, or below 2 or 3 standard deviations. So, for example, if I wanted to know the probability that a data value is above 1 standard deviation or below -1 standard deviation from the mean, we would take 100% of the data, because that's how much data we have, 100% of it, and then we would subtract out that middle, the 68%, because that's not being included, and we end up with 32. Then, because it's the middle 68%, each side is even, they're the same. So if I have 32% of the data left over, so if I cut that in half, I end up with 16%. So that means above 1 standard deviation is 16%. And below -1 standard deviation is also 16%. And then if you were to add 16 plus 34 plus 34 plus 16, you would end up with 100%, because that's the whole, all of the data. We can do the same thing to figure out what percent of the data fall above 2 standard deviations or below -2. So again, we would have 100% of the data. We subtract the middle 95%, leaving us with 5% left over. If I cut that in half, I then end up with 2.5%. So this would be 2.5%, and this would be 2.5%, because it's going to be equal on both sides. And then same thing for the 99.7. We have 100% of the data. And if I were to subtract 99.7% of it, we end up with 0.3. Again, it's even on both sides, so if I cut that in half, we end up with 0.15%. So above 3 is 0.15%, and below -3 is 0.15%. So the empirical rule is really nice in this regard, because we're able to figure out exactly what probabilities fall, because we can use these approximations. If you have data that is normally distributed, 68% is within 1 standard deviation, 95% of the data fall within 2 standard deviations, and 99.7% will fall within 3 standard deviations of the mean. The other thing that we can do with the empirical rule here too is we can actually even then use these values to find the areas here. So if I want to figure out what percent of data fall between 1 and 2 standard deviations, well, I can take my 16% and subtract my 2.5, and I end up with 13.5%. And because it's in the middle, This area and this area are equal, so this is also 13.5%. I can do the same thing to find in between 2 and 3 standard deviations. I can take 2.5 and subtract 0.15, and we end up with 2.35 on both sides because it's even on both sides. So in both cases, there's 2.35% in between 2 and 3 standard deviations. So the empirical rule kind of helps us make these calculations without having to use a calculator or the table. It's really nice. Now, this only works, though, if you are exactly 1, 2, or 3 standard deviations from the mean. So if we're not, then that's when we have to use the table or the calculator. And to determine how many standard deviations we are from the mean, we use the z-score. So just as a recap, this is the equation for the z-score, where z equals x minus x bar over s, where x is your data value, x bar is your mean, and s is your standard deviation, which I'm still abbreviating because it's too long to write out. So let's just recap that and kind of practice calculating z-scores with number 1. So for number 1, they tell us that the grades on a statistics midterm for a high school are normally distributed with a mean of 81 and a standard deviation of 6.3. We want to calculate the z-scores for each of these exam grades. So part A, the exam grade is 65. That's below the mean, so that should tell me that I will end up with a negative z-score. So z is going to equal, my data value is 65 minus my mean of 81 divided by the standard deviation of 6.3, which gives me a z-score of negative 2.54. For B, the z-score will be equal to the data value of 83, which is above the mean, so I should end up with a positive z-score here, minus 81 divided by 6.3, and z will equal 0.317. So again, it's positive. And then C would be similar. We have a data value of 93 minus 81 divided by 6.3, which gives us a z-score of 1.91. When you are calculating z-scores, go to 2 decimal places. You can go further if you want to, but the table only goes out to 2, so that's all you really need. You can use more on the calculator, but it won't make that big of a difference.